Okay, so let's do an example here with another type of collision. Okay, so let's say that we have a mass m1 and another mass m2. So let's say that m1 is going to be 1.21 kilograms. Let's say that m2 is going to be 2.64 kilograms. And so let's say that m1 is moving with some initial velocity v1, and let's say that the other object is sitting stationary. Now, what's going to happen is that mass 1 is going to run into mass 2. Now, let's say that when it does run into it, it sticks together. So they're sticky, and it sticks together, and these two objects move together as one object afterwards. So now it's going to be the total mass is m1 plus m2, moving as one object. All right, so we want to solve this problem. Well, initial momentum equals final momentum. So initially it's m1v1, all right, and then at the end it's m1 plus m2 times that final velocity. So the final velocity is m1v1 divided by m1 plus m2. So that's going to be equal to 1.21 kilograms times v1, and I don't remember if I told you, but let's say that the initial velocity was 3.35 meters per second. So 3.35 meters per second divided by 1.21 kilograms plus 2.64 kilograms. And that comes out to be 1.05 meters per second. So we had the original object, m1, moving with an initial velocity of 3.35 meters per second, and we had m2 right here. Okay, m1 was 1.21 kilograms, m2 2.64 kilograms, and then after they stuck together, the two objects together were moving at 1.05 meters per second. So now let's think about energy. So let's consider the initial kinetic energy. The initial kinetic energy, only mass 1 was moving, so that's 1/2 m1 v1 squared. So that's going to be 1/2 times 1.21 kilograms times 3.35 meter per second squared. And so that comes out to be 6.79 joules. Now, the final kinetic energy is 1/2 m1 plus m2 times v squared, because the two were moving together, okay, as one object right there. So 1/2 times 1.21 kilograms plus 2.64 kilograms times 1.05 meter per second, and that's squared, and that comes out to be 2.12 joules. Okay, notice the initial and final kinetic energies are not the same. There was a change in kinetic energy. So the change in kinetic energy, that's going to be K final minus K initial. So the change in kinetic energy was going to be 2.12 joules minus 6.79 joules. So the change in kinetic energy was a minus 4.69 joules. So there was a loss of kinetic energy. Now, the energy did not go into potential energy, so that means we actually lost mechanical energy. Well, where did the energy go? Well, the shock of the two objects slamming into each other actually causes their molecules to vibrate, so they're actually warmer afterwards. There's also the possibility as they hit that some sound waves were created, and so some of the energy may have gone away as sound. Okay, so there's a variety of different places the energy could have gone other than as kinetic or potential. So, but this does mean that we lost mechanical energy in the problem. Okay, so there's less kinetic energy afterwards. This means, and this is very important, in solving a problem of this sort, you cannot use conservation of energy to solve the problem. Because some of the energy is going places that you're not looking. Okay, now that's a very important statement right here, because frequently in a collision problem, students are just programmed, I don't know if it's from high school or what, to use conservation of energy to solve the problem, but it will not give you the right answer because mechanical energy is not conserved in this problem. So that means conservation of energy is the wrong way of solving the problem, unless you take into account the change in temperature and the sound waves and all that other stuff. Then you cannot use conservation of energy, and we don't have to take care of all that right now. So that for a collision problem, you must approach the problem in the form of only using conservation momentum. Now, that's not to say that energy is always not conserved, or mechanical energy is not always conserved. There are certain kinds of situations, for example, where two objects come together and they interact using only non-conservative forces, and then they move off afterwards. And in that case, the kinetic energy at the beginning equals the kinetic energy at the end. Now, this is a specialized case that only involves certain kinds of interactions. The interactions we had before didn't apply. So how do you differentiate? Well, in physics, we use a term, elastic collision or inelastic collision. So what is the difference between elastic and inelastic collision? Well, with an elastic collision, the initial kinetic energy equals the final kinetic energy. For an inelastic collision, the initial kinetic energy is not equal to the final kinetic energy. Now, we know energy is conserved in the big picture, but that means some of the energy is likely going into those non-conservative forces, so some of the energy is going into other forms. And so this unless you know for a fact that you have an elastic collision, you assume inelastic. Now, it can be shown, and it's a little beyond what I want to spend time here doing, and that is if the two objects stick together and move as one, then that is the situation in which you have the biggest difference in kinetic energy. Okay, and in that case, we call it a perfectly inelastic collision. So a perfectly inelastic collision is when the two objects stick together. That's the example that we just did. And in that case, the final kinetic energy was, in fact, less than the initial kinetic energy. And so there's your special case right there. All right, so this is how energy and collisions relate. So I'll do some examples here with these different kinds of collisions.